vosotros ya habéis venido alguna vez, y en esta ocasión pues es una bonita ocasión para recibir a una astrofísica, en realidad es una geóloga planetaria que está de camino por Europa. Os voy a contar un poco datos biográficos de ella. Se llama Graziella Caprarelli. ¿Eso qué, no?
Yeah.
He intentado aprendérmelo a la italiana. Y bueno, ella estudió toda su formación en Italia, en Europa, pero luego, aprovechando una estancia postdoctoral en Japón, conoció allí a su marido, que es australiano, y bueno, que se dedica a temas de biología, investigación en el cáncer, investigación sobre el tratamiento del cáncer, tal como me acaba de contar hace un momentito. Y la vida la llevó a vivir a Australia, donde lleva ya desde el año 1994 trabajando en el Centro de Astrofísica, que se llama Centre for Astrophysics de Australia, en Queensland, y bueno, trabajando en todo lo relacionado con el sistema solar. El sistema solar, como bien sabéis, es un lugar de observación, nuestro hogar, el sitio en el que vivimos, y las investigaciones que se hacen sobre él son a las que se tiene mejor acceso desde el punto de vista de las ondas espaciales, porque podemos viajar al sistema solar, podemos movernos por el sistema solar, podemos enviar naves, podemos incluso aterrizar en algunos de los mundos rocosos del sistema solar. Y por este motivo es uno de los campos más de moda también dentro de la investigación de la geología planetaria, de la astrofísica también, tan importante como la búsqueda de planetas extrasolares o como los temas cosmológicos. Graziella hoy nos va a hablar precisamente de lo que está escrito ahí, la distribución de agua y hielo en el sistema solar. Es una especialista muy importante en el mundo sobre este tema. La conferencia va a ser en inglés porque ella al ser italiana y vive en Australia, prefiere hacerlo en inglés y por eso lo va a hacer en inglés. Luego al final de la charla, si queréis hacer alguna pregunta o necesitáis ayuda con el inglés, no hay problema, os traduciremos. Ella también entiende un poco de español, entiendes un poco de español y espero que sea una charla estupenda, como estoy seguro que va a ser. Muchas gracias y Graciela, por favor. Please, confía en your turn.
Thank you. So, gracias por la introducción. I don't know. Thank you very much for that very kind introduction. I hope I will speak slowly. I'm pretty sure English is understood by the majority of people in Spain. At least that's been my experience traveling around. I never had any problems. Everyone always understood me. Hopefully, even if I am not terribly clear, by speaking in English, you'll see some interesting pictures. And I have some writings on the slides as well, so that may help, even if my accent is too strong or it doesn't come across very easily when I speak, but you can refer to the things that are written. I think we will have questions at the end because this is being streamed live as well. But if at any point during the talk you feel like you cannot proceed unless something is clarified, just make yourself known, make some noise and ask a question. With that, let's get started. So as for the introduction, I work mostly on the distribution of ice and water in the solar system. But I started as a terrestrial geologist. So my background is studying volcanoes on Earth. Yet, little by little, I became interested in using the knowledge that I accumulated by studying Earth to other planets. And in fact, since 2001, I have been working also at NASA. This is when we started getting interesting views of the Martian surface. with a number of missions, starting with Mars Global Surveyor. And it was obvious to me that as an Earth geologist, we could contribute a lot to understanding and interpreting the data that were coming out from Mars. So since then, I have not looked back, and I have continued working with Mars scientific team, specifically with the Mars Express missions. Initially, the high-resolution stereo camera, hence my affiliation with the International Research School of Planetary Sciences in Italy. And then with the ground-penetrating radar on board Mars Express, MARSIS, which penetrates through the surface and allows us to see what's underneath. And I have been working mostly at the beginning looking for geological structures under the surface, and then became involved with looking for the distribution of water and ice in the subsurface with my colleagues in Italy. So the talk today focuses particularly on the distribution of ice and water on Mars. I will talk towards the end about our discovery of liquid water at the base of the southern polar cap of Mars. But before that, I want to make a general introduction to where water and ice are in the solar system, why, and why it is difficult to find water on Mars. Makes sense to everyone? Yes, I'm communicating. So why do we look for liquid water and ice in the first place? Why do we care? Certainly because the only planet where we know that there is life is Earth. And we know that life requires water. So there is a direct link between the presence of water and life on our planet. Water is essential for life as we know it. But nowadays, there is also renewed interest in figuring out where liquid water and ice are in the solar system, because we are thinking of sending humans to colonize, establish settlements on the moon, on Mars, possibly beyond. And water and ice are necessary for survival of human avamposts. And so a lot of resource exploration now with the moon and Mars actually centers on water and ice. So there are two reasons. Therefore, in this talk, I will briefly introduce this last point, how water and ice are relevant to our missions of expansion in the solar system. But then I want to dedicate more time to the concept of habitability of planets, which relates to the presence of water and ice. And so I will talk about the distribution of water and ice in the solar system to end up with Mars. So ISRU stands for in-situ resource utilization. This is essentially the idea by which human missions to the moon and to Mars will be molded on. The idea being that we send the humans to the moon, to Mars, possibly beyond, but they will have to survive on the resources that they find in situ, so in that location. Therefore, there is this preliminary work of us scientists on Earth mapping the distribution of these resources. And that's why the work of geologists is also important in interpreting the data that come from the moon and from Mars specifically, but also beyond. So you may remember, if you are as old as I am, 54 years ago, we had the first landing of humans on the moon. And then soon after, in the same time, in the same year, we had more missions landing on the moon. We haven't been to the moon since 1972, unfortunately. These were short trips, 3 days, 4 days at the maximum, where the astronauts went to the moon, landed with everything brought from Earth for their survival. Very difficult situations, of course. It requires really an incredible gene pool of humans to be able to go there. But there is incredible support, mostly from Earth. These were the concepts for human exploration 54 years ago. However, and this is the moon, the new exploration is one which has in mind the fact that we want to send humans back to the moon, and there they will try to establish bases, avant-posts, for longer term durations. And in that case, that's where we start to think, we need to start thinking how these people will survive and what resources they can find on the moon to survive and build avant-posts of humans there. So we know that the moon itself is very challenging. There is no atmosphere, so no one can breathe, and there is no liquid water on the surface. But we know that there are some areas of the moon where ice has been found. And of course, having the proper equipment, if you have ice, which is solid water, you can melt it to obtain water, you can extract oxygen, you can extract hydrogen to use as fuel. So ice is also extremely important. However, in the side of the moon that faces us, we cannot see any ice. But there was a very interesting experiment which was carried out when the Lunar Crater Observation and Sensing Satellite, the mission LCROSS, went to the moon. And they did an interesting experiment by basically launching a projectile to the surface of the moon and then analyzing the vaporized material that came out of that impact. And they could determine that there was some ice, some water. They could determine with mass spectrometry that there was some water that could be detected from the regolith, that is, from the soil that had been impacted in this experiment. Of course, it's very little. It was just a whiff of water, but it was enough to start us thinking about the possibility of finding cold ice traps on the moon. And in this particular case, we were looking at a location which is near the south pole of the moon, where it's very, very cold, in a crater called Cabeus. That's going to be also one of the candidates for future missions to Mars. In these locations, and here, this is Cabeus, where the impact happened, there and there. These are areas near the south pole of the moon, which are perennially in shadow. So the sun doesn't hit there at all. And so that's where some cold traps are possible, where ice can concentrate and be accessible. So the exploration from humans will certainly focus around these permanently dark areas near the South Pole. Modeling, in this particular case, this is a paper which was published in Nature Astronomy in 2021, where the authors have actually modeled all the possible locations where the ice, which are in perennial shade, and therefore where ice could be located. And there are mappers experiments. There is OH abundance. Now, OH is one of the hydroxyls. That's one of the components of the molecule of water. So in principle, where you find abundance of OH, you can interpret that as meaning that there could be water as well. Could be included in minerals. There are minerals that have also water in their structure, but it is important also in that case. With the mapper, they noticed, these authors, that there is a relationship between latitude and the abundance of this tracer of water, the hydroxyls OH, and that this abundance increases going towards the poles. Again, confirmation that if you move towards the South Pole, you are likely to find more hydrous material. However, when everything is said and done, if you do all your calculations, you can find that there is only less than 2 by 10 to the minus 10% of water present, of these hydroxyls present in the upper surface layers of the moon. And when you compare this with the Earth, 2 multiplied by 10 to minus 2, you can see that the moon doesn't have that much water at all. So there are hydroxyls there, there may be water, ice, it's not a lot. You would have to squeeze a lot of rocks to extract some water. That's why, again, you concentrate your attention towards those regions of the moon where, again, the perennial shade may act as cold traps so that there can be a concentration of this water as ice in those locations. And I like particularly the work by these authors. This is actually an experiment which was run from Earth, where a Sophia is an instrument on board of an aeroplane, flew across the United States. They were actually just wanting to test the instrument, and they pointed it towards the moon at that time. And even in testing, they realized that at the wavelength of 6 microns that this instrument actually provided pointing towards the moon, they could detect an increased abundance of this interference for this wavelength. Meaning, and this is a wavelength which is typical of water as a molecule. So in this case, therefore, the authors concluded that there is actually molecular water, so water as a molecule, not as hydroxyls as part of the minerals, but actual molecules of water, and that the distribution, these are huge error bars here, but in any case, it's particularly relevant at the mid to high latitudes of the moon, again, going towards the South Pole. The next question then is, how is this water present? Where is it exactly? And there are two possibilities. It may be drops of water which are trapped in the glass that forms when meteorites impact on the surface of the moon and therefore melt a little bit of the surface. This melt becomes glass, and some molecules of water may be trapped in this glass. Or it might be, which would be the better option for us, molecules of water that are trapped in the soil and therefore easy to extract. Again, there is evidence, therefore, of water on the moon, but we need to find for the specific locations where it's actually concentrated. So we talk often about the new mission, the Artemis program, NASA, which plans to put humans again and to have them land at the South Pole by the end of 2024. Fingers crossed. The crew has been selected, and these are the lucky astronauts. We'll see what happens. The mission had been pushed a little bit back because of COVID and the number of problems, naturally. And sending humans to the moons is not easy, as we all know. And we want them to actually go there in a targeted location, this time to look for ice, not just to set foot on the moon and test technology. So good luck to them, and we are waiting for this mission with bated breath, literally. So far, so good, everybody? Yeah, fantastic. So, having dispensed with the issue of in situ resource utilization, and I usually tell everybody that yes, there are all these mining companies now that wish to go to the moon or to Mars to extract metals or to use meteorites to extract iron, rare earth elements, etc. Those are the resources they're after. But in my opinion, the most precious resource without which nothing can happen is in fact water, is in fact ice. And therefore the search for water and ice is the most important aspect that can happen at this point in time, even with regard to thinking for the future in terms of other types of resources. Having dispensed with that topic, I want to move on to the actual science that interests me. So why there is a certain distribution of water and ice in the solar system, why Earth is an ocean planet when we compare it to Mars. So let's start and try and figure this out. The first concept I want to introduce is that of the snow line. Now, first, before we get to the snow line, we want to talk a little bit about where the planetary object in the solar system exist. We know that we classify them generally in two different types of classification, by type and by location. So by type, we know that there is a sun. This is our primary in astronomical terms. Then we have the periodic objects, the planets. The planets in the solar system are subdivided into terrestrial, like Earth, Jovian, like Jupiter, and dwarf planets, like Pluto, for example, now. Then we have the moons that are also planetary objects, but it's just that they revolve around another planet, and then together with the planet, they revolve around the sun. Then there are asteroids, which in the solar system are mostly located in the asteroid belt between Mars and Jupiter. Then we have comets coming all the way from the Kuiper belt. And then we have non-periodic objects that do not have a trajectory which is predictable around the sun. They can shoot out from outer space, their orbits decay. So rogue asteroids, the ones that cause catastrophes when they impact on the surface of a planet, and non-periodic comets are among these. But we can also subdivide the solar system objects by location. So we have an inner system where we find our primary, the sun, and then where we find our terrestrial planets, Earth as well. So starting from the sun, we have Mercury, we have Venus, we have Earth, and then we have Mars. Then the moons of these planets, and then the asteroid belt, which is between Mars and Jupiter, as I mentioned. And then in the outer system, we have the gas giants and ice giants. So we have Jupiter, we have Saturn, etc. And then we have the centers, which are asteroids, which are beyond, and dwarf planets, which are beyond the inner system. They're moons that revolve around these giant planets, and other asteroids, the Trojans, for example. Then we have trans-Neptunian objects. And among the trans-Neptunian objects, which means beyond the orbit of Neptune, we have the Kuiper belt, other dwarf planets. And enveloping all of this is the Oort cloud. Now, from here to here, the orbits of all these objects are located more or less along a flat plane. But the Oort cloud instead is spherically distributed around our solar system. So this is a little bit of an image where we have the sun more or less in the center here, and the Kuiper belt all the way outside. As I mentioned earlier, it has a kind of a flat disk distribution. Here there are locations of some of the spacecrafts that over the various decades have been launched from Earth and have reached the end of the solar system. Particularly, I'm thinking of the Voyagers, which are now beyond the sphere of influence of the Sun, the heliosphere. Essentially, that's the distribution of the material around the Sun. Now, most of the ice, as you can imagine, water ice and other types of ice, are located, as a matter of fact, in the Kuiper belt. So the Kuiper belt is a huge mass of condensed volatiles, including water. But what happens closer to the Sun in the solar system? So I like to always use Earth as our parameter for comparison with everything. So in this table, you can see that there are the planets, other objects as well. Earth is here, and every parameter related to the axis, the orbital axis, the orbital period, so how many days it takes for the Earth to revolve around the Sun, the mass, the radius, and the rotation period, etc., is given as 1. So essentially, what we are doing in this table is we are taking the length of the orbital semi-major axis for Earth, dividing it by itself, and it gives me 1. And then I do the same with all the other planets and other objects, and divided by the Earth's orbital semi-major axis. So I can see that Mercury is closer to the Sun, Venus is closer to the Sun, Mars is farther, etc., etc. Clear how this table works? Everyone still awake? Yes! Let's do it. Okay. So taking Earth as a reference, and that's why we talk often about comparative planetology, because we compare planets to what we know about Earth, we have to look at the distribution of the different objects, how different they are, going from closer to the Sun, which is somewhere here in this table, and then farther away from the Sun. So closer to the Sun, we have rocks. We have those objects that are similar to Earth, like rocks, like terrestrial objects. And then as we move farther away, we have ices. In other words, those worlds where volatiles, including H2O, are condensed and form ices. So why is there this kind of distribution? There is a concept in astronomy and astrophysics, which is that of the snow line. Sometimes you may have heard of it referred also as the frost line or the ice line, but it's the same concept. And by definition, it is the distance from the protostar, and this refers to the beginning of the formation of a star system, in our case, the solar system, where the temperatures away from the protostar, away from the early Sun, were low enough for compounds like water, ammonia, methane, CO2, and CO, which are all volatiles, to condense into solid ice. In other words, closer to the Sun, they would not be able to condense because it's too hot. And so once you reach the snow line, a distance, a specific distance from the Sun, then all these compounds can condense into solid ice. And you can easily see that if they condense, then they can give origin to planetary bodies, which mostly are composed of this material. So the snow line, of course, the position depends on the star. It exists in every star system, but the position of the snow line will be different depending on the size of the star. So the position also of the snow line will determine the number and position of rocky, Earth-like planets, versus the icy, the Jupiter-like planetary bodies in the solar system. So it also determines how many Earth-like planets and how many Jupiter and Uranus type planets will exist in a star system. And a lot of exoplanetary research, in fact, deals particularly with the position of the snow line to try and figure out in those systems if there are worlds similar to Earth. So far, so good? Great. Now, it's intuitive to figure out that, therefore, if we are closer to the sun, within, therefore, the boundary of the snow line, we will have mostly rocks because the volatile compounds would not have condensed. Whereas if we are beyond the snow line in our solar system, we will have condensed volatiles, and so that's where we expect to have a lot of ice and water ice as well. So this is simply a diagram that says pretty much the same thing that I said before. At the time of formation of the solar system, the temperatures clearly close to the sun, and this is the distance from the sun. Here we are closer to the sun, here we are farther, closer, farther, closer, farther. At the time of formation of the planets, condensation of material, the temperatures were so high close to the sun that only metals, and by that we also mean the rocks, can condense. And that's why the bodies like Earth, all the way Mercury, Venus, Earth, and Mars actually could solidify as rocks. The snow line in our solar system more or less corresponds to this distance here. And this is where we find Jupiter, Saturn, and all the other giants, which are hydrogen rich and are basically gas and icy bodies. Make sense to everyone? We are just saying the same thing in a different way. So if we look at this artist impression of the solar system, everyone can see the sun. This is the asteroid belt here, here, and here. And so within the asteroid belt is the inner solar system, and outside is the outer solar system. We have that these planetary bodies, again Mercury, Venus, Earth, and Mars, this is the moon of Earth, formed in these conditions at the beginning of the formation of the solar system, whereas outside in the outer solar system, beyond the snow line, you have all the other bodies where you have condensed volatiles. So, for example, we have a mission going to the Jupiter system now, looking to find if underneath the icy crust of Europa, which is one of the satellites of Jupiter, there may be a liquid ocean, which is what we think based on our model. So this is Europa's surface, which is solid icy crust. There is heat coming from within the planet, or in this case it's a satellite, but it's a planetary body, so that possibly there may be a salt-rich ocean immediately under the crust, where we hope to penetrate with our ground-penetrating radar RIME now on JUICE, the mission. There is another world, in this case a satellite of Saturn, Enceladus, which also shows an icy crust, and where also we hypothesize that there may be an ocean underneath. In this case, this is a very interesting geological proposition. The heat that actually keeps the water liquid under the ice may be derived from mineral reactions. So from minerals that are found underneath, metamorphosing, reacting, even in the solid state. These reactions produce heat, and this endogenic heat might actually be able to provide these kinds of hot spots in a liquid ocean. Another world that we need to explore. And of course, we have nice images of comets. The farther we go outside of the snow line, the more ice we find, and comets have certainly a certain percentage of ice. So far, so good, everyone? Now then, let's get closer to us, and therefore let's zero in on Mars. But first we have to define the terrestrial planetary bodies. So what are they? They are the inner solar system bodies: Mercury, Venus, Earth, Mars, and our moon, as I've already mentioned many times. They are rocky, hence terrestrial. So they formed, just as a reminder, in this part of the solar system, when the solar system was being formed, where the temperatures were very high. And therefore we expect all of these planetary bodies to be rocky and to be dry. They are all more or less formed in a similar fashion in terms of their structure. So this is Earth as a reference again. This is the crust. We call it crust in geological terms. It's basically where we walk. So this is the ocean. Underneath the crust, we geologists talk about the mantle. Now the mantle moves as a viscous type of fluid, which in some areas is also molten, and that molten part is what drives volcanic activity on Earth. And then the inner part of our planet and of terrestrial planets is what we call a core. And on Earth, there is an outer core which envelops the innermost core. Now we think, and we know in fact, that the outer core is partly fluid, and the movement of this fluid in the outer core, which is mostly composed of metals, including iron and nickel alloys, contributes and produces the geomagnetic field of Earth. So it's thanks to what's inside our planet that we are protected by the solar wind, by the ionized particle, by the plasma that comes from the sun, which gets trapped in the geomagnetic field around Earth. However, having said all of this, and that there are similarities in all these terrestrial planets, they are more or less all the same in terms of their structure, and they formed in the inner solar system, so they should be dry. What do we find? That Earth, our planet, in fact, is wet. So we have to try and explain this. Why is Earth wet? Well, you will hear that the reason why Earth is so peculiar is because of its geological activity. So Earth is an active planet which is still dissipating the initial heat of accretion. At the time of accretion, every planet engulfs a certain amount of gravitational and differentiation heat, and this heat gets progressively dissipated over billions of years. On Earth, this process is still ongoing because Earth has a relatively large mass, and by relatively I mean relative to Mars or relative to the Moon, and furthermore, its mantle is structured in such a way that it is double layered, and this double layering acts also as an insulation that slowly allows release of the heat through volcanic activity, meaning that the Earth is still active nowadays. Mars, as we know, also had a very active volcanic history, but at the moment Mars has no active volcanoes because Mars is smaller, it lost its heat much, much faster. And that's why we say that size matters, even though Mars is composed of the same type of material than Earth. But size matters also for another reason. We may have heard, all of us, that Mars has a very thin atmosphere. So basically, you cannot breathe on Mars. There is a very tiny veneer of atmosphere, and this atmosphere is mostly CO2. So it's very different from Earth, where we have an atmosphere which we breathe, is mostly nitrogen and oxygen, so we can survive on Earth very well. But why this difference? Again, it's about the size. When we look at Earth and Mars, Mars has about 1/3 of the gravity of Earth. It's a smaller planet. So because of that, the molecules that remain in the gaseous state achieve escape velocity on Mars much more easily than on Earth. So molecules like water, ammonia, and methane particularly achieve escape velocity on Mars and are lost into space. They don't remain enveloped around the planet. Whereas with Earth, as well as with Venus, the higher gravity keeps those light molecules around the planet, so that once the atmosphere is formed, then it stays, and it's nitrogen, it's oxygen, it's water, it stays enveloped around the planet. So this diagram is read in a way where everything that is below the diagram relative to a planet is available in the atmosphere of that planet, and everything that is above is not available. So for example, while Neptune, Uranus, Saturn, Jupiter have a lot of hydrogen and helium, in fact they are gas and ice planets, there is very little of these around the atmosphere of Earth and Venus. But we have lots of water vapor, we have ammonia, we have methane, whereas Mars, everything that is above there is not available. Make sense to everyone? Cool. So Mars may have had an atmosphere in the past. Because of the volcanic activity, it may have also produced juvenile water, so water that comes from the depth of the planet, which is also the origin of a lot of water on Earth at the present day as well. Juvenile water comes out of volcanic activity, though there may have been lots of incoming water from comets at the beginning of the history of the planet, which remained trapped. With Mars, Mars lost its initial atmosphere very, very early on, and it never acquired it again for these reasons here. So again, geological activity is very important also for Earth to produce more water and particularly to keep this water liquid at the surface, thanks to a mild, at least it used to be, greenhouse effect. Make sense to everyone so far? So Earth is different and it is unique for its position relative to the Sun, its size, the fact that it's still active geologically, and therefore it is an ocean planet in spite of the fact that it's located in the inner solar system. So when we concentrate on Mars, we see some of the parameters that I mentioned earlier about Mars being different from Earth. So its escape velocity, which I mentioned earlier about the molecules of gas, about half that of Earth, about a third the gravity for that reason, temperatures, this is the mean, clearly very low, and a very small surface pressure. And that atmosphere that exerts that surface pressure is mostly CO2. So Mars is a hyperarid desert. If we compare at the present day Earth and Mars, and of course this is not to scale, and if we were to distribute all the water on Earth around Earth, creating a uniform layer, which we otherwise call as the global equivalent layer, GEL, then the depth, the thickness of this layer would be 2 kilometers on Earth, but only about 10-40 meters on Mars. So you can see how different Mars and how dry it is relative to Earth. Even if we calculate back, based on models of volcanic activity and evolution of Mars, even then, early Mars would not have had more than half kilometer thick gel. Again, even at the time of its formation, when a lot of volcanic activity existed, when there were comets coming all over, only half kilometer of global equivalent layer of water was available on Mars. Mars is therefore very different from Earth. And that's why it's difficult to, and we require special instrumentation to look for water anywhere on Mars, on the surface, in the subsurface, because there isn't any. So finding it is very difficult, whatever is there, whatever traces. Of course, we know that there is a lot of water ice at the poles, but the poles on Mars are funny and they are very, very cold. So we don't expect there to be any possibility of melt at those latitudes at the polar caps of Mars that could give us liquid water. But one of the purposes of our mission was precisely, with the ground-penetrating radar MARSIS, was precisely to look for liquid water where the polar caps are, elsewhere as well, but particularly where the polar caps are, to see if a microenvironment which might become closer to even the glacial conditions of Earth would allow for some presence of liquid water. And that's our research, where we come to our research. Now, one would think, okay, if we take the fact that there is ice at the poles of Mars, so there may be some increase of temperatures because there are seasons on Mars as well, and when we increase the temperature, then we can melt some of the ice, then it becomes liquid, we might pond it, we might find it. But we see from the phase diagram of water that all of you certainly studied at school, that if we take the conditions at the surface of Mars, which are represented by this little m here, meaning that water on Mars would be present only as solid on the surface, and just increase the temperature, we end up straight in the vapor phase. So we don't melt it, we don't create liquid. And once you make the molecules of water vapor, they escape to space. As we saw in that earlier diagram, anything that is gaseous molecular water does not remain enveloped around Mars, it escapes to space. And so Mars has been steadily losing its water to space, even the one that is at the polar caps. The only way that from Mars you can achieve conditions like those on Earth, for example, where we know that liquid water exists, is by increasing both temperature and pressure. So you must find or think of a mechanism whereby you somehow increase the atmospheric pressure of Mars. How do you do that? Because we've already said that the atmosphere of Mars is very, very thin. So how do you increase that pressure? Well, we know that the rotation axis of Mars, and this happens also for Earth, but to a lesser extent, oscillates quite significantly. So Mars goes from periods of very low obliquity, where the rotation axis of the planet is almost vertical, if you look at it from the ecliptic, to being very, very inclined. And when Mars' rotation axis is very inclined, the poles are closer to the Sun than in this situation. So we think that because in the history of Mars, this situation of high obliquity has occurred many, many times and periodically, then we would have had many periods lasting about hundreds of thousands of years where there was enhanced sublimation of molecules of water from the polar caps facing the Sun, and this water could have formed a transient high pressure atmosphere. So this is simply calculations that show how often the oscillations and the obliquity has changed over the past few million years. And so when you have those situations, you actually can create in a transient manner, so it's not permanent, but high atmospheric humidity conditions. And when that happens, you have that ice ages are formed on Mars. There is more ice extending also towards the lower latitudes near the equator, and there you can even have liquid water. And we know that this has happened because we see morphologies on the surface of Mars which remind us of rivers like the ones we have on Earth. And so there must have been free-flowing water on the surface of Mars. And this is what we call ancient ice. So it spread even in these latitudes. So this is just an image of the surface of Mars, in which you may recognize Olympus Mons, the highest volcano in the solar system, the Tharsis Montes, other recent volcanoes. This is Valles Marineris here. But we have been able to detect, also with the ground penetrating radar, some evidence of ice buried still underneath here that was probably formed and deposited in those high obliquity period. And another way that we studied the presence of ice under the surface is by looking at the shape of the ejecta of impact craters. So this is particularly a study from a former postdoc of mine, and we made the cover of JGR Planets that time, where we can see that the impactor hit the surface of Mars, and clearly there must have been fluid in the impacted subsurface to create this ejecta around. So that's ancient ice. But what about modern ice? This is where our MARSIS, ground penetrating radar, comes into play. So what is underneath the South Polar Cap? And here I'm going to show you a little video. All right, so that was a nice video that the European Space Agency made after we published this paper here, where we published about the detection of subglacial water bodies underneath the South Pole of Mars, the South Polar Cap, using MARSIS, which is our ground penetrating radar. This is the team. The team is composed importantly by geologists like myself, physicists and engineers. We all have to collaborate. We have Roberto Rosei, who is the principal investigator for MARSIS in relationship to the European Space Agency and co-principal investigator in relationship to NASA. Elena Pettinelli, who is the physicist who leads the scientific team. Andrea Cicchetti, mission control in Rome. So all of us and Sebastian Lauro, who is one of the main modelers who actually devised a new probabilistic method to interpret the signals that we obtain from this location of Mars called Ultimi Scopuli. So this is all the South Pole of Mars, all the region, the South Polar region. This is what we see as ice, mostly CO2 ice on the top, but all of this area is in fact water ice. And in this specific location, this little blue polygon here is where we have outlined the area where there are multiple liquid bodies of water underneath 1.5 kilometers of ice. And we have substantiated this discovery and further experimented, running also experimental work with a number of papers. And since we published our papers, then there have been 2 other groups independent of us who also suggested that the surface shape of the polar ice in this location supports the idea that there is liquid water underneath. So these are simply topographic profiles. So they show the variation in elevation of the South Polar Cap along 2 directions, this one and this one. And according to these other authors with recent publications, they say that the shape of the topography here, so what they see on the surface, supports the presence of liquid water underneath, which is basically what we had detected with our instrument. So we published a number of papers in response to other groups that suggested that the reflections of the ground penetrating radar that we observed could be due to other processes, but in a number of publications, which I'm not going to bore you with, we specified that, and we ran other experiments showing that those alternative interpretations are not viable. And the only way that we can understand the bright reflections that we observed with the radar is that there is liquid water. And thus far, no alternative group has provided us with an alternative interpretation that we have tested and modeled and simulated for that is viable. So brines, in this case, liquid water with an elevated salt content, and that's important because the salt content depresses the melting point of water, so that even in very, very cold temperatures like those at the base of the South Polar Cap, they can be liquid. And so we also provided additional modeling that also clarifies why MARSIS, the ground penetrating radar on board Mars Express, sees the reflections, whereas SHARAD, which is another ground penetrating radar on Mars Reconnaissance Orbiter, another NASA-run mission, cannot. The 2 radars, SHARAD and MARSIS, operate at different frequencies. SHARAD operates at higher frequencies than our instruments, and that means that the signal through the ice for SHARAD is attenuated, so it's not as strong, and that's why SHARAD does not see those reflections. So we explain that in another paper, addressing therefore other concerns. So how does MARSIS work? This is very simple in reality. So this is the flight path of Mars Express. MARSIS, the ground penetrating radar, is on board Mars Express and sends down radar signals. Some of these radar signals are then reflected back by the surface and intercepted by the spacecraft as it moves along its flight path. But some of the signal penetrates through the crust, and when it intersects a material of different physical properties, it gets reflected back up. And when we find liquid water, we have a very strong reflection back. That's why we think and we know that we intercepted water, because the reflections at those locations in Ultimi Scopuli were much, much stronger than anything else we saw elsewhere, and they were even stronger than the surface reflection. So that's just animated to show the different rays that then return. As I mentioned, that's just another perspective of the same location in the little polygon. And this is, again, it's like a cross section, except it's made from the radar signal This is the surface of Mars at Ultimis Scopuli. These are the layers underneath 1.5 kilometers that generate the very strong reflections, which here you can see in this diagram. This red is the surface backscattered reflection. This is coming from the depth from here. That can only be liquid water. So that's the position that we mentioned. There are a number of parameters that we have explored as well to corroborate. So it's not just the intensity of the signal, but also the acuity, how smooth the signal here is. And we can see some location where we didn't find water. The signals are very different from the signals that we get in the locations where we found water. This is the map that we published, where the dielectric permittivity, which is the geophysical parameter that we pick with the radar, indicates the locations in blue where there is liquid water. And this is one that's about 30 kilometers by 20 kilometers across. Around here we have at least 3 other liquid bodies of water about 10 kilometers across. And so that's published also in our Nature Astronomy paper. Just to give an idea of what it would look like, and this is the last bit, we have here the surface of the ice in the location where underneath we found the bright reflection. And so if we could see through, we would see 4 little lake-like bodies of water. And in 3 dimensions, if you have the surface here, then 1.5 kilometers below the ice, so all this black here is ice, is where the little lakes are. So we can now transfer the knowledge of the science of our mission, but also of the technology of our mission, how we were able to work with the signals from the radar to detect those bright reflections, because it took a mode of acquisition of the data that's different from standard. And we can now transfer all this knowledge to the next mission, JUICE, which I mentioned in the beginning, to the ocean worlds. This is again Europa, and on board of JUICE there is in fact a radar, RIME, and RIME is just the acronym for Radar for Icy Moon Exploration. It works at different operational frequencies than MARSIS. So this is 9 megahertz, which is between the frequency of MARSIS and Charade. So we think that's good frequency to penetrate through the ice shell of Europa and see if there is an ocean underneath. The antenna is 16 meters long, and this is the deployment of the antenna just last week, which was successful after a week or so where the antenna seemed stuck. Eventually it got deployed, so we're very happy about this, and the launch of the mission JUICE last month. And with this, I thank you so much for your attention, and I hope I didn't put you to sleep, and I hope that you may have found something stimulating in this talk. Thank you. You can use this. Yeah, I heard. Yes, I heard.
Bueno, ¿alguna pregunta queréis? Levantáis la mano. Sí.
Hola, voy a hacer la pregunta en español. Muchas gracias por la charla. Me preguntaba sobre la Mars Express, si ha sido capaz de escanear toda la superficie de Marte o hay algún sitio donde podría haber todavía depósitos de agua por encontrar.
Yes. So Mars Express has been operating around Mars since 2003, and it has a suite of instruments on board. So the ground penetrating radar is one of them, but there are 7 experiments overall. One of the experiments is the high resolution stereo camera, and the camera has imaged the entire surface of Mars already at a very good resolution for geological studies, better than 12.5 meter per pixel. So each pixel of images is 12.5 meters in resolution, which is very good. The peculiarity of the high-resolution stereo camera is that it can acquire images over very large areas, and so it's possible to follow features like morphologies, geological boundaries, over geologically significant distances, which other more highly resolving cameras do not allow to do, because they can only image very tiny areas sparse between. So Mars Express has actually achieved most, if not all, of its primary scientific goals. And I am happy to say that the mission has now been extended, because after detecting the water, now we have the knowledge again to use the radar in a certain way, so that we want to explore more. And the European Space Agency has supported the extension of the mission. So the mission has been operating since 2003, the radar since 2005, so we've been everywhere on Mars. I think there's a question. Oh.
Gracias. Mi pregunta es si cabría la posibilidad de que haya agua en el cinturón de Kuiper o en la nube de Oort.
Yes, we certainly think that there is plenty of water ice in the Kuiper belt and in the Oort cloud. That's where comets, most comets, come from, and they are made of ice. Yes, definitely. We know that there is lots of volatile ice, including water ice, but also other types of ice.
Okay, I'm gonna try to say my question in English. We have the opportunity of getting water from underneath the surface of the Moon and Mars. In particular, in the Moon is extracting from rocks. Are there environmental damages from this action?
Yes. Certainly,
especially in the Moon, no? Because
yeah. So on the Moon, we are looking at cold traps where those perennially shaded regions could have water ice on the surface as well as in the regolith, in the pores of the soil. So naturally, if it's in the pores of the soils, we have to disturb the soil to extract it, but it may be also just on the surface as a patina of ice around particles, but inevitably we are going to disturb it. There's no question there. So with regard to Mars, where we found the liquid bodies of water that's beneath 1.5 kilometers of ice at the South Pole. We are never gonna go there because the southern hemisphere of Mars is much higher in elevation than near the equator and the northern hemisphere. That means that as thin the atmosphere of Mars is globally, it is even thinner at those higher elevations. And therefore we cannot land anything there because we cannot parachute anything in very thin atmosphere. There's not enough aerobraking. So everything that you launch is gonna crash. So we're never gonna go there, which is why we continue to study the equatorial regions for the ancient water that's underground, but maybe not so deep so that we can reach it. And there are some dusty glaciers, so there is a possibility even now of glaciers that formed in the past but have been covered by dust, so they're kind of protected over the years, millions of years, and maybe that ice is still accessible to us, because otherwise we would be looking at the depth underneath the surface near the equator for the ice ground table of 1 kilometer. We're not going to reach 1 kilometer underneath, we're not going to dig that. But in these debris-covered glaciers, maybe it's possible to get, there is still ice just scraping through the surface. That's why it's important to look everywhere and looking also at the ancient ice that may still be there. Again, if we do that, we disturb it.
Thank you.
Thank you for all the explanations. It was really great. Just a simple question. You're trying to find life on Earth, but through the way about finding water. But there is another possibility to find if there was life before in Mars. But that's kind of the best way to find it.
So if I understood correctly, there may have been past life on Mars, and we should look at traces of that past life rather than looking for life now. That is not easy to find. There could just be only where the water is, and we don't know how to reach it. That's a very good question. In fact, a lot of colleagues of mine who are paleontologists, they are focusing on studying some concretions or some shapes in minerals that may be traces of activities of biological life. So maybe some kind of bacteria or some kind of organisms that also interact with the rock, disturb the rock a little bit, so we can see traces of that. And for that, there are lots of what we call analog studies on Earth. For example, in Australia, in the Pilbara stromatolites, that we think that these kind of organisms, if they existed on Mars, may have left a similar kind of trace in the rocks. And so those colleagues of mine are looking also at sending on Mars instruments, landers, that can look at within these rocks for those kind of shapes. So that requires particular intelligence of the robots to be able to identify certain shapes. But that's also research that is happening.
Grazie mille.
Prego.
So thank you, Graziella, for this interesting lesson.
You're Italian?
Yeah.
Okay, parla italiano.
Well, in English, just for all. And speaking about juice, what type of sensors or characteristics are we looking for on Europe or on Jupiter icy moons? Just what will be able to characterize us for the water and the organic molecules could be in the water?
Yeah, so there are a number of instruments, again, on the mission JUICE. Of course, I'm familiar with the radar mostly, but definitely there are spectrometers, So everything that you already have on the Mars Express missions, Mars Global Surveyor, Mars Reconnaissance Orbiter, the suites of those instruments for spectrometry, imagery, etc., is also on JUICE. And therefore, yes, with our instruments, essentially, it is a matter of figuring out there is an ocean, liquid underneath the crust. Can the radar penetrate through this crust? And based on what we learned on Mars, we may try to understand also if the ocean that exists is salty. If it's salty, probability of life, yes, better than if it is just fresh water, for a number of exobiological reasons that I am not an expert on, but I trust my colleagues. And then naturally, there will be spectrometers that determine compositions of molecules. So there is a range of experiments that will happen. Now, obviously, we have to wait 8 years because the mission has to reach the system. Until then, it will be our students who continue the research. But yes, everything, well, a lot of things have been planned for that mission as well.
Ok, grazie.
Prego.
Well, thank you very much, Graziella.
You're
It was a pleasure for us to be here, and hopefully you will be back sometime somewhere.
Nice.
We will follow your investigation, your researches, and thank you very much.
Thank you. Thank you all for staying so late. Thanks a lot.
Muchas gracias.